This presentation is for the International Conference for Internet Technology and Secured Transactions. This is an alternative round-robin CPU scheduling algorithm with average burst time dependent time quantum. My name is Zach Bedell. This paper is also contributed to by Aspen Olmsted from the Department of Computer Science at College of Charleston in Charleston, South Carolina. First, we'll take a look at general operating system information. An operating system is a collection of programs and utilities that act as an interface between end users and system hardware. Modern operating systems have evolved into a multitasking environment capable of running several processes concurrently. As programs advance and get more complicated, there's more demand on our CPU. And so because of that, process scheduling is one of the most important tasks of the operating system. A program in execution is called a process. This can come from an application that has multiple processes, all requiring resources from the CPU. While waiting its turn to be fetched by a CPU, a process is put into something called a ready queue, which is a data structure that operates in a first in, first out manner. Process scheduling algorithms are designed to increase CPU speed and efficiency. They are designed to handle multiple process requests in a manner that provides a fair distribution of resources amongst each process. There are several different process scheduling algorithms, which we will go over. These are classified as either non-preemptive or preemptive. Some examples of non-preemptive are first come, first serve, shortest job first, and priority. Priority-based algorithms can either be preemptive or non-preemptive. Some examples of preemptive algorithms are shortest remaining time next and round robin. Sometimes these can lead to higher context switches, which is the process of a CPU switching from one process to another. The metrics involved in CPU process scheduling include burst time, which is defined as the amount of total execution time required by a process. Turnaround time, which is the difference between completion time and arrival time. Wait time per process is the time that the process completes. The difference between that and process arrival time minus the burst time. Context switches, as we just mentioned, is the number of times the CPU switches to another process. It's good to lower the amount of context switches because context switches include overhead involved in fetching and storing in memory. Throughput is the number of processes completed per the execution time. So basically the amount of time or the amount of processes that can be completed within a certain window of time. And then finally, response time, which is defined as the time period between when a process arrives and when the first response on that request starts. This is affected by average waiting time of all the processes before a respective process in the ready queue. Typically, we want to reduce the number of all of these metrics. Just a quick overview of the first come, first serve non-preemptive algorithm. This algorithm chooses the order of execution based on earliest arrival time. Once a process starts, it does not stop until it is complete. That's the definition of a non-preemptive algorithm. Some disadvantages of first come, first serve is that process importance doesn't matter. If a smaller process of less importance is working for a long time. There might be a system crash, and a more important process behind it might never get executed. First come, first serve also results in high wait times, and parallelization and multi-threading is not possible and results in poor resource utilization. This can result in the convoy effect, which is many processes with a short burst time being stuck behind a process holding that resource for a long time. Another non-preemptive algorithm is shortest job first. This algorithm chooses the order of execution based on the shortest process burst time. As we said, it is non-preemptive, and its advantages are the fact that it improves upon the wait time from first come, first serve, and does have better resource allocation and CPU utilization, which is a main goal of scheduling algorithms. Some disadvantages are that it can cause starvation due to several short jobs in a ready queue. And a big problem is that many operating systems really don't have a way to determine the burst time. There's no mechanism within an operating system typically to determine burst time. There are some that can estimate it, but that is an assumption that this algorithm has to make, that they're able to estimate it. Another non-preemptive or preemptive algorithm is the priority-based scheduler. This chooses the order of execution based on priorities that are assigned to each incoming process. Processes with the same priority are executed in a first-come, first-served manner. Some advantages of this algorithm is that it is relatively simple to implement and understand, and it is great for environments with multiple process burst times and time requirements. Unfortunately, this is also prone to starvation, and as before, low priority processes are at a particular risk of starvation. A preemptive algorithm is shortest remaining time next. This is very similar to shortest job first, except that it is preemptive. This focuses on the remaining burst time after a process is on the CPU for a certain amount of time and then gets put back into the ready queue. A CPU using this algorithm will switch back to that based on evaluating all of the other processes in the ready queue and choosing the one with the shortest remaining time next versus the total burst time. This algorithm does have the advantage of higher throughput, and shorter jobs do finish quickly because of this design. Some disadvantages include higher wait times, like first come, first serve, but particularly for larger processes. And again, operating systems must be able to estimate the burst length for this algorithm to be effective. Finally, we come to round robin. Round robin is the most commonly used algorithm in processor allocation because it more fairly distributes resources across all processes by assigning equal priority to each. It assigns that priority by use of a time quantum, which determines the amount of CPU utilization per cycle. A general rule of thumb is that 80% of process CPU burst should be shorter than whatever time quantum is chosen. Advantages include higher throughput, and like our last algorithm, shorter jobs finish quickly. The disadvantages, however, are high number of context switches. Since there is that static time quantum, it continually switches no matter how long the burst time of that process is until that process is finished. And too low of a time quantum degenerates round robin into first come, first serve. That static time quantum ends up also leading to high wait times. A bit of previous work that we focused on for this paper was done by Behera and others. It is focused on something called the multidynamic time quantum round robin. Basically, this was a version of round robin that adjusted time quantum dynamically twice through a cycle, and it based it on where each process in the ready queue lies in a list that is sorted in order of increasing burst times. Processes with burst times less than or equal to the median burst times of all processes are assigned a time quantum equal to the median burst time. Once we move past that median, the quantum is assigned to the sum of all burst times of processes in the upper quartile of burst times. So basically, it finds a sum of all processes with burst times greater than 75% of the rest of burst times. They found that this method improves all performance metrics by calculating burst times twice, and other proposed methods calculate time quantum only once, and they found this to be a great improvement on regular round robin. We found the disadvantages to be that many processes are needed in the ready queue for the algorithm to work effectively. Our proposed algorithm is based on average of highest burst times. We thought we could improve upon wait times and execution times. Based on the 80% rule of thumb that was just mentioned, we hypothesized that larger quantums would provide better performance metrics than short ones, but that taking a sum of the upper quartile of burst times, as in Behera's method, may be resulting in higher than necessary wait time and execution times. So we first sort the ready queue in ascending order of burst times, similar to Behera. But then instead of taking the upper quartile, we calculated, or the sum of all in the upper quartile, we calculated the average burst time of all processes with burst times higher than 90% of all burst times in the ready queue. So we took that top 90%, took the average, and then set all of the burst times in the ready queue to that average. A little bit more on our average method. In terms of the implementation, we implemented several alternate methods to compare how well our average method was doing. We implemented a standard round robin, which is denoted by SRR. Behera's method is denoted by DYN, stands for dynamic. Individual was one we designed, which sets the total burst time for each individual process to its own burst time divided by 4, which would result in a pretty small, but not the smallest, burst time. For a min method, we took all processes and assigned them a quantum that was the minimum burst time of all processes in the ready queue. And max was the same as min, except it was the maximum burst time. Our min and max methods were really meant to be controls to see the two extremes. A little bit more on implementation. What you'll see in figure 1 is the pseudocode for creating processes in the ready queue. before processes were sent to each of these methods for testing, I created 300 processes with ascending burst times. I took the counter as 1, multiplied the counter by 20, and then added that again to the counter. This ready queue was sent to each algorithm 2,000 times. The reason we did that is because it was implemented in Java. The Java documentation says that there is not exact nanosecond accuracy, and we couldn't use milliseconds because it was not an accurate enough simulation because of the speed that these executed. After we sent each ready queue 2,000 times to each algorithm, metrics were averaged across each of the 2,000 iterations and then ordered. The results were as follows. What you see highlighted in yellow is the top performing. You can see that our average method performed better in wait times and execution times, and as good as the other top 3 algorithms. To conclude our experiment, we saw algorithms with a larger time quantum perform better consistently than all those with a short quantum. And though we did achieve good results with the average method, there was no improvement in context switches from the following best 3 algorithm comparisons. But it does appear to compensate for the drawbacks of the higher waiting time and standard max and the multidynamic time quantum round robin methods. There were a number of limitations in this simulation, such as in a real-time operating system, processes arrive at varying times, and they often arrive while a process is currently running. We left out the mechanisms for handling arrival time while a process is running to make the code more lightweight and to more isolate our results and make them more consistent. Burst times were also consistent in value and order across each iteration. That goes back to the process for creating our ready queue. They were the same values each time, whereas in a real-time operating system, they would have multiple varying arrival times and more varying and unordered burst times, which could affect results. The overhead for calculating average and burst times and the sorting by burst times was excluded in the overall performance measurements, again to isolate simply how the algorithm worked and get away from the exact implementation in the language we were using, which was Java, and we wanted it to be machine independent, and we wanted to avoid basically any outside influences that might affect our results. The memory access times were also simulated. Every time a real system makes a context switch, it has to fetch and store from memory and to memory. And this performance can be changed depending on which language we were using or which language is used for a simulation. Again, we were using Java, but some future work might be in C, which gives more direct access to memory, and that might improve it. Lastly, here is our references.